Hi, ladies and gentlemen. In the last class, we discussed the statistical averages and we understood the meaning of statistical averages and we understood how we make decisions based on statistical expectation. Then we saw the St. Petersburg paradox, which a demonstration of which revealed that expectations are not the only benchmark for decisions. So today we see another very important property of random variables and events, that is the entropy of a random variable. Let me start with that presentation. This speech is organized into your learning outcomes, definition of entropy, and then the entropy of a coin toss. We will see a plot of this, and then we will see the compute the entropy of a uniform random variable, then the summary of understanding. So you will learn the concept of entropy and you will compute the entropy of uniform random variable. Now the entropy of Gaussian random variables are very important because I told you in the last classes that most of the channels they have a Gaussian noise, and we will use this to compute the entropy of the received signal. Randomness, entropy and information are synonymous words. They represent more or less the same thing. Events and random variables have entropy. The concept of entropy was put forward by the great scientist Boltzmann, but unfortunately it was ill-timed in the way that this was proposed even before the atom model, and most people couldn't understand what Boltzmann put forward in his theory. So nobody accepted it, and Boltzmann was depressed by it, and he committed suicide. And it was very tragical. Anyway, the entropy of a discrete random variable in bits, like if it's a discrete random variable like a coin toss, that is defined as it is usually marked with the letter capital H, that is Hx, that is equal to sigma pi log 1 by pi or minus sigma pi log pi. This log 1 by pi is actually called the information. Okay, that is a self-information. The log 1 by pi or minus log pi is called self-information. Say for example, if I have a switch with two states, say on and off, its information in that switch is log 1 by 0.5, okay, and that is log 2 to the base 2, which is 1 bit. Okay, so if I have a switch, it has got 1 bit of information. If I put two switches in parallel, I have 4 possibilities, like both of them on, both of them off, one of them is on the other way, the other one is on and the first one is off. So I have possibilities like 0, 0, 0, 1, 1, 0 and 1, 1. I have 4 possibilities. So what happens is there is log 4 to the base 2, which is 2 bit. Okay. So one bit has an information of one switch has an information of 1 bit, and two switches have information of 2 bits. So that information usually it is I, that is log 1 by pi or minus log pi. This is a sigma pi into information I. So basically this entropy is nothing but the expected value of the self-information. So for the time being you understand this way, minus sigma pi log pi. So entropy of a continuous random variable with a PDF fx alpha, this is hx is minus infinity to infinity with a minus sign, fx log fx, or minus infinity to infinity integral fx alpha log 1 by fx alpha d alpha. Okay, here I put a negative sign instead of the 1 by fx, I put as fx with a negative sign. So the entropy of a continuous random variable x is hx, that is in negative of minus infinity to infinity fx alpha log fx alpha d alpha. Okay. This log minus log fx alpha is called the information, and the expectation of that thing is called the entropy. So entropy is actually the average or expected value of information in a system. So this is a great concept. So if you compute the entropy of, let us consider a coin toss in which the probability of head is p and the probability of tail is naturally 1 minus p. So I have two outcomes there. So we have to take these outcomes separately and sum them up. So that hx is, this is a discrete kind of random variable. So the entropy is hx is minus sigma pi log pi. So it becomes minus p log p minus 1 minus p log 1 minus p. Okay. hx is minus p log p. It is minus 1 minus p log 1 minus p. Okay. So if I plot this along with probability p varies from 0 to 1. So how does this entropy varies? How does this entropy vary with p? You can observe this plot. Okay. You can see that when p equal to 0, its value is here it is 0 multiplied by something, this is 0, and here it is 1 minus 0, 1 times log 1, log 1 is a 0. So all these things are measured in bits. So it is said that here it is log to the base 2, so that I can measure in bits. So when p equal to 0, the entropy is 0. So when p equal to 0 means it's an impossible event. For the impossible event, the entropy is 0. The average information is 0. So likewise, when p equal to 1, here this term is a log 1, so it's a 0, and here it is a 1 minus 1, that's a 0. So again, hx is 0. With p equal to 1 means it is a sure event. For the sure event also, you can see that the entropy is minimum, entropy is 0. Okay. Now, when does it get the maximum? When it reaches equiprobable case, that is when p equal to 0.5. When p equal to 0.5, you can see that it is minus 0.5 log 0.5. So it is 0.5 log 2 to the base 2. It is 0.5 log 2 to the base 2. Minus 1 minus 0.5, that's a 0.5 log again 0.5, so it becomes 0.5 plus 0.5, so which is a 1. So you can see that the entropy becomes maximum here. At p equal to 0, the entropy is minimum, it rises slowly, and when p equal to 0.5, it reaches a maximum and again falls down here. When p equal to 1, again it becomes a 0. Now I will show you the code with which I plotted this thing. Here you can see that I import the pylab module, which is nothing but the matplotlib plotting libraries, and I import the scipy module. So here I have a p from some 0.001. I didn't put a 0 here. So 0.0001 to 1 with an increment of 0.001. So here hx is computed this way, minus 1 p log p. Again I multiplied by divided by log 2 to make it in bits. Minus 1 minus p log 1 minus p. Again I divided by log 2 to the base e, so that this h is computed in bits. So then I plot this, then I put some grid on it and put a label and everything. And I save this figure as a entropy plot.eps. Now we can run this code and you can appreciate this. You can see this curve. So this is the shape of the entropy curve. Entropy is a convex function. I will come to that. Now let me go back to my presentation. So what if it is a uniform random variable? Now when we talk about a uniform random variable, we know that it's a continuous type distribution. So hx is minus negative of minus infinity to infinity integral fx alpha log fx alpha. So this uniform distribution means some a to b, it is 1 by b minus a. So everywhere else the value is 0. So this integral defaults to a to b. Magnitude is 1 by b minus a log 1 by b minus a, because fx value is 1 by b minus a in the interval a b. So that this becomes 1 by b minus a into b minus a into log 1 by b minus a. Okay, with a negative sign. Oh, I forgot the negative sign here. So it becomes a log b minus a bits. I forgot a minus sign here. You have to put that minus sign. It is 1 by b minus a into log 1 by b minus a. So log b minus a bits. That is the information in terms of bits. Now, what is the entropy of a Gaussian random variable? This is very important, because this is how I compute the information transmission through a channel. Because I told you there is something called the central limit theorem, which makes the additive noise in a channel Gaussian in distribution. So the entropy is the self-same equation, negative of minus infinity to infinity fx alpha log fx alpha d alpha. So let us consider a zero mean Gaussian random variable. Zero means it is the mu value is 0. So and the variance is sigma square. So it is fx alpha is 1 by root 2 pi sigma square e raised to minus alpha square. Sigma mu is 0. Alpha minus mu, that mu equals 0. So it becomes e raised to minus alpha square by 2 sigma square. So I compute the logarithm of this one. So this becomes log fx alpha becomes minus, I compute this logarithm, that is log 1 by root 2 pi sigma square. It becomes a minus log root 2 pi sigma square. Then minus logarithm of this becomes the exponential goes, and it becomes minus alpha square by 2 sigma square. Now I have to multiply this fx with log fx alpha. So it becomes hx is log root 2 pi sigma square fx alpha d alpha plus 1 by 2 sigma square minus infinity to infinity alpha square fx alpha d alpha. Okay. Now you can see that this log root 2 pi sigma square is a constant value. Then inside this integral it is minus infinity to infinity fx alpha d alpha, which is 1, because it is a total integral of a probability density function. You know that it is 1. The area under the probability density function is a 1. So that it is log root 2 pi sigma square into 1. So that is this term. Plus here it is 1 by root 2 pi 2 sigma square into integral minus infinity to infinity alpha square fx alpha d alpha. Now we are considering a zero mean Gaussian process. So it is basically integral minus infinity to infinity alpha square fx alpha d alpha is nothing but the variance sigma square. Earlier we said the second order central moment. It is a sigma square. So this sigma square is cancelled by this sigma square, so that I have log root 2 pi sigma square plus half. This half is nothing but log root 2 pi sigma square plus log root e. Okay, it is log root e, meaning that if I combine this together, it becomes log root 2 pi e sigma square in natural logarithms. You can convert by multiplying by log 2 to the base e and put it in bits. Okay. So this is a entropy. This is a natural logarithm. You can convert this to bits. So this is how the entropy of a Gaussian variable looks like. Now the entropy of properties of entropy is always a positive function. You saw that it's always a positive function. Xx is always greater than 0, and the entropy is a convex function. I don't go into the mathematics of a convex function, just I will give you some simple examples. See, in a convex function, if I draw a chord or a line between 2 points, then the line will be contained by that surface. Say for example, this is a convex function. This is a circle, this is a convex function. If I take any arc across this, say if I write a chord from this point to this point, or any point in the circle, that line will be contained by this circle. So that's a convex function. This line, straight line, is a convex function. Say I take any 2 points and draw a line connecting these 2 points, then the new line will be contained by the first line. So this is also a convex function. This is a case with entropy. This has a shape like this. So you take any point between these two points in the curve, that line will be contained by this surface. That's the meaning of the convexity. So, but if you say the thing like this is not a convex function, because if I take a line here, it is contained by the surface. But if I take 2 points here and draw a line here, this is outside this region, outside this function. This is not a convex function. This is not a convex function because if I draw a line between these 2 points, that is outside this surface. So this is not a convex function. Anyway, entropy is a convex function. Now coming to the end, in this video you understood the concept of entropy, then you computed the entropy of uniform and Gaussian random variables. For the Gaussian random variable, you see that the entropy is log root 2 pi sigma square E. And that's the end of this presentation. I thank you all.